Okay, hello again. So let's start with the second presentation of Dennis, who is working. We work together in data engineering team in Bolt. Let me escape from the speakers. And yeah, so you heard the story about how we do machine learning and A/B testing machine learning in Bolt. Now Dennis is going to tell a bit more about the infrastructure behind it. So let's start.
Hey, how's it going? So I'm Dennis. I'm a software engineer here at Bolt. And today we're going to learn how to scale data science and how do we approach it at Bolt. So we're going to cover a few things. We'll touch a bit, thanks to Elizabeth, I don't have to do introduction of Bolt, so this part is done, tick. I'm going to touch a bit what kind of data science problems we actually have at Bolt and how do we, well, just what kind of we have. And we're going to talk about how do we actually scale data science with the data science platform that we are developing right now. And we'll dive deeper into the architecture of one of the pieces of software that helps us to do so. Before that, please raise a hand if you work in a company that has at least one machine learning model running in production. Oh God, that's amazing. Look around. That's beautiful. That's perfect. I'm super excited. Then you'll probably know the problems that I'm going to talk about. So this is great. Before we dive in, Before we dive in, I actually want to get together on the definition. What does it mean to scale data science? Does it mean running distributed TensorFlow? Does it mean training on huge data sets? I would say no. To me, scaling data science is not large-scale machine learning. Of course, the latter is the part of the former, but that's not the proper way to approach the problem, in my opinion. Plus, oh my God. So the clicker is, sorry. Yeah. So in my opinion, scaling data science is to improve the ability of your team to learn from the data and automate and improve your product based on data-driven decisions and machine learning. And you don't need to have a huge team of data scientists to scale your capability to data science. If you make one data scientist more productive, you already scale it. So who of you have been to the North Star AI conference this year? Oh, all right. So some of you, less. The goal of North Star AI is to solve the AI talent shortage in the region. And we can do it in many ways. We can bring more people from abroad. We can train more people here. But one of the ways to solve it is to make the talent that we already have more productive and make them accomplish more with less. So that's kind of, oh my God, there are so many spoilers. Yeah, so imagine a data scientist coming fresh out of college or a person transferring from some other role in the industry. They think that real life is like Kaggle. You will download some CSV dataset somewhere. You maybe do some resampling. You do feature engineering. You clean the data. And then you optimize your model. You get your validation score up to the sky or down to the floor. Depends what metric you optimize for. And life is beautiful. And maybe in the end, you just make a report, publish a blog post, or, I don't know, make a nice sample application. But in real life, no matter is it big or small company, you need to deal a lot of this, getting the data from all the kind of sources that you have in your company or organization. You need to not just train model once, but you need to have a way to repeatedly train and refresh the model. So, and that's a bit different problem. And in my opinion, the situation looks even more like this. You think that it's going to be like that, but it takes twice as long, and it takes at least twice as many people that you have. So if you're in a small startup, maybe you are doing all of that by yourself. Maybe you have engineers solving some parts of that for your data scientists, but still there's a lot of labor and engineering that goes into making a successful machine learning project. And this is actually what data scientists care about. And that's kind of what they are trained to do. And this is actually something that solves the problem. Defining the problem, finding the metric that you want to optimize, finding the right problem to solve, and solving this with machine learning and analysis and tools. So, yeah. And what's the reason behind it, actually? That something, if you start learning about machine learning, you get to learn pandas, you get to learn SciPy, NumPy, and all this stuff. You get to train some model, do some pretty visualization, clean the data, whatever. That's what data scientists are taught to, and that's what you think is real machine learning. What happens in real life is that to run the model successfully in the systems that delivers the value to your users, you need to have a lot of things happening around. And all of them are quite, even if you don't develop them yourself, you need to integrate, you need to run and manage and maintain. And that's a lot of work. So now let's come back to what Bolt does and why data science matters to us and why we invest a lot of time and effort to build the tools for that. We optimize many things using data science and machine learning. We optimize our marketing. We optimize pricing to balance supply and demand in the cities. We also optimize the way we match cars with the passengers. We fight fraud, build our own mapping infrastructure, and many things more. And all of these problems are very unique and very different. And that's why people that we hire to solve them have different background, have different skill set, different knowledge. And if with every problem there is a huge tail of infrastructure you need to build, it will be a lot of infrastructure. That's why we will want to unify it and make it easier to solve any problem inside a Bolt. That's why we're working on data science platform. And if you look really simply, it has few main components. First, we have a data. I mean, there is no data science for data, or somebody disagrees with me. No? Nobody raised hands, because I will hunt you later. So we store our data in many different sources, including our data warehouse, data lake. We have operational databases from where we replicate data, and we have a lot of it. But data, raw data, is usually of no use to machine learning. And you need to have some pre-processing steps that enable you to feed the data into machine learning models or into the brains of humans and decision makers. And of course, when we build models, we need to train them, we need to deploy them, validate them, monitor, and scale. And to do that, all of that, you need to be sure that the data that you're using is of high quality and you can trust this data. And also, it's easier to explore and visualize this data and have tools for that. So, I've been talking about data science in vacuum, like Rainbow, whatever data science is that. Let's get down to some simple problems and see what kind of challenges you may face. And for machine learning, like one of the problems of data science is machine learning. And any machine learning model needs features. And they need it both for training and for prediction. And usually you would get it from somewhere. You would have some pre-processing step, both for training and prediction. So it's fairly easy, right? It's like you can specify all the machine learning in one diagram. Let's look at the two examples of machine learning where it's easy and where it's not. In the first example, I'll use super rough simplification, but let's turn on the imagination. Who knows DuckDuckGo? Okay, so that's the search engine that doesn't track you. Cool. Imagine that I want to find a sushi bar in Tallinn and I want to eat. So I type in sushi bar Tallinn and I send the request. It also sends my IP address and some other stuff, but let's focus just on the text that I typed into search bar. Usually search is a really hard problem, but for the now, let's imagine that DuckDuckGo has a model that predicts what's the probability of person to type some search entry to click on the ad related to restaurants, for example, because they have person who publish ads, like some restaurant publish their ad, and they want to know, should they show me the ad? Will I click on it? Will they earn money? So they can have some simple or fancy NLP, and analyze the text that we are having here, like sushi bar Tallinn, and they can say that there is quite high probability that I might want to go and check out the website of a restaurant. Now let's come to the example from the Bolt. You open an app, you are in the Bolt office, you want to go to Tallinn airport or wherever you want to go. And we also know where are the available drivers. And we need to show you this estimated time of arrival. How much time it will take for a car to get and pick you up. This all sounds simple. You have the place where the car needs to arrive, and you have a place where the driver is. So you can probably do some simple approximation, right? But actually to do this accurately, you need to know a lot of data about the city, about the drivers. So you may need to know how much the traffic is in this district at this time of the day. You might need to know the driver. Is this driver a fast guy who cut all the corners and turn when it's like double stripe and go on the red, and that's why he arrives like 2 minutes faster than average driver? Or maybe he's like really slow and, I don't know, goes 20 kilometers per hour on a highway. So there are many things that you might want to know, and to compute them, you will actually need to have a lot of compute, and it may take a lot of time. If you want to aggregate all the trip history of a particular driver, this is something you cannot do in real time on the production database. For example, we use MariaDB, and our DBA will kill me if I would try to do that in real time. Because we have a lot of these requests, and they have to be fast. And there are many more use cases when the features that you need are not available in request, or they are hard to extract from the sources that you have easily. Our answer to that is a feature store. Who of you have heard about feature store concept? Wow, a lot. Cool. So we're gonna talk about how we implemented our version of feature store and what problems it solves for us. But for those who will learn this concept today, feature store is kind of a place where data scientists or developers define the features that they will need in future. The feature store will do the computation of these features on behalf of the user, so that the features are ready when somebody will need to request them. One of the most important properties, in my opinion, of having feature store is that data scientists can easily reuse features developed by other people, by other data scientists. So if my friend has developed a feature that is useful to my project, I can just use it, basically for free. And that's how that's like scaling data science. You scale the knowledge of one data scientist to several problems. And one of the sweet parts for developers who consume the predictions of this model, you don't need to change any code, because you just say, give me prediction for this model, for this user, and let it figure out. And it all gathers the data needed. And it all sounds super nice, right? Fancy stuff. Yay. So that's our feature store version 1, something that we had in the last year. It's pretty simple, right? Like just three objects, 2 errors, like, right? Everybody can do that. Just a small note. We at Bolt, we have Redshift, which is AWS-based kind of massively parallel columnar storage. It's like a data warehouse solution. We use it to replicate their data from our microservices and our production databases. And our data scientists and analysts and like BI tools have access to this thing. So first version of feature store, we just have a set of queries that are written somewhere in our backend code that are executed with cron jobs in the backend services, and they select these features and they push them to Redis. So we may have, for example, for users and drivers, we can have like many dozens of queries defined. Each of them computes some number of features, and they are all merged together then in Redis. Redis is a in-memory fast in-memory key-value storage. Many people use it for cache. We use it kind of as a storage with super low latency, and the data is available through an API. So I can come and say, give me please all the information about this user and tell me what feature he has or she has, driver has. So with this thing, we already solved few problems that are related to scaling the capability to do data science. Well, first of all, services don't need to know anything about features. They just need to know that I need this prediction for this user. And our services figure it out, where to get this data, which features are used, which features are not. And also, it's kind of a uniform way and uniform place where you get all the features. So it's kind of nice. You don't need to write 5 different pipelines to get the features for your model. So it's much less engineering effort needed. But as any great software, when it start using, you get to bump into scale problems and people problems and everything else. So the jobs that compute features became slow, really slow. And it was really kind of expensive operational overhead. When data scientists would ask to implement a new feature from our team, they would send us a query in Slack. We would take it, copy paste it, refactor it, maybe combine it with some other queries for efficiency, and then we can push it. And that was kind of a mess. And also the jobs were, because they were slow, they were timeouts, and it was difficult to manage. And also there was no visibility. Like if Elizaveta would ask me, What kind of features I have for this rider, I wouldn't be able to say so, because otherwise I would have to SSH into machine, and that's something that we cannot do. Yeah, and we have like many scalability issues there. But I think the most important problem in data science, in scaling data science, is not technical problems. You can buy more machines, you can parallelize work. It's more about people problem, and how do you define the process so that data scientists are more productive and can get their experiments ready faster. So we decided we have a problem of ownership, that people who develop the feature, the code that extracts features, are not the people who actually implement it and put it into production. We wanted to change that. We wanted data scientists to own the code that compute the features. So we come up with the JSON-like config, where data scientists specify the query that extracts the feature that they care. For example, this query just gets one feature, right count, obvious, simple. And some description so that other people can read it and find out whether there are some limitations of this feature, where it can be applied. And we have like a bunch of those queries for users, for drivers, and many other entities that we have. Using this, we were able to give the tools to data scientists and analysts to come up with their own features, and we just need to push it to production. So it made our job much easier, and it made time from idea of feature to production much faster. Like instead of weeks and months, now it's days. First, I do need to talk when we come to the slow part. When I said the jobs became slow, there is a small reason behind it, or big reason. So Redshift is a massively parallel thing. It has one leader node, and it has many compute nodes that actually store the data and do the job of processing, sorting the data, running aggregations. Redshift is really, really cool for analytical queries or some aggregated queries. When you need to get one or few numbers sliced and diced by a lot of dimensions, when you need to join 20 tables, it's super powerful. But the problem comes that we need a lot of numbers. We need to get all the features from all of our riders outside of Redshift. And in this case, leader node becomes the bottleneck, and streaming the data from there becomes extremely slow. And that was like quite a painful thing for us. So we were working hard, and that's kind of our version 2 feature store right now. So here I'll go, it may be a bit technical, so you can ask me right now if I don't explain something well. Now, instead of getting all the data out of the Redshift, we compute each of the query runs, and it stores its slice of we call it profile. It's slice of user profiles or whatever kind of entity it's computing features for. So we have like many tables inside Redshift. Then we merge them together in one large and wide table with all the features, and we have a huge table. And we also store it so that data scientists can use it for training. The same kind of features that are computed for training go into serving, which is cool. And we unload this data to S3. And unloading means that instead of going through the leader node and going to my app, it will in parallel, each of the compute nodes will in parallel write to S3. And this is much faster. Instead of hours, it takes minutes. So that was like really, really big improvement in performance. Okay. Yes. So that was part number 1. Part number 2. Actually, instead of just asking for features for entity, like for example for rider or driver, some of the teams asked us, could you please solve the reverse problem? Instead of getting the features for user, can we get all the users who match the features? Let's get and do it fast. And we were like, yeah, sure, no problem, guys. Just give us time. So we introduced second data storage. So we still store the features in Redis, but we also replicate the stream of features coming from the S3 into another queue that is like basically duplicate the data, and we push them. We have workers that put them to Redis and Elasticsearch. And through the simple API, you can get the features that you need, and also you can get the IDs or entities of users who match certain search criteria. And this is super powerful thing. Yeah, and also one of the funny things about Redis is that our data scientists we teach them the best practices of software engineering, and that's why they write really good feature names. So this could be whatever, let's imagine, number of participants who visited meetup. And if we want to improve the efficiency of our meetup, we'll have a number of participants who stay till the end of the meetup or whatever. So the feature name actually can take like 30 characters or something. And when you store it to Redis, it's kind of like a JSON. So the actual feature is just one number, but the feature name is like 30 characters. So it could take much more space than actual features. And because of that, our Redis machine was growing and growing and growing. So we had to introduce compression. And by being an efficient team and doing kind of the 28 folding 28 rule, we implemented quite a simple way. We had just, for each feature, there was like a hard-coded one or two like ASCII symbols. So we just have like a simple map of compression and decompression for each feature. This is like a simple trick, and we are not ashamed to do that because it solves the problem, and this is like as efficient as you would think about using libraries. So by this way, we can tame the Redis and keep it of a reasonable size while still growing the amount of features and amount of users. So that's kind of the current state, and it's kind of work in progress. There are many, many more things that we'll implement here, but kind of the story behind this is that by building something like that, we're able to get faster from idea to production. So from the moment that data scientists write a new feature, it can be available the next day, and they can deploy the model right after that. So now the experimentation phase is much faster and it's much easier. We have also many parts of data science platform, like model deployment, model training, up to automation. So by combining all of that, we can rapidly decrease the time from the moment when the model sits in the Jupyter notebook till it hits the production and somebody starts to query it. Yeah, also we reduce the job time like by many, many times. And the coolest thing, which I think is something that everybody should strive for, is to reduce the features, because that's the part of scaling data science. For example, smart data scientists spend days to come up with useful features that describe something about our business really well, and we want to reuse it. We want others not to copy-paste the code, not to go through this process again, but just take what's up there and be faster. And when you write a good software, it starts being used by use cases that you did not imagine. In our case, other teams were using it as an easy-to-integrate tool for building data pipelines and having some aggregated things stored in a really useful way. And also something that I was super excited to see actually is that one day, product manager came to our data scientist and asked a question. Can we predict something about our riders? Can we predict that these riders are corporate users that company pay for their rides? And data scientists were able just to get the dump of our feature store from the Redshift. They cleaned up, like deleted some features that were not useful for them, and just they've done some wrangling. And in 2 hours, they built a model that had pretty good predictive power. And this is something that we should strive for. We give a tool so that it's super easy to get from the idea to something working and improve from that. So that's kind of was the tada moment that, yay, it's working. That's where it should go. So coming back to the scaling of data science and reducing the overhead of the infrastructure. We cut out some of the parts like developing infra. Now it's much faster and you can repeat on the work of others when you develop new models. It's easier to collect the data and it's easier to add new features. And that's kind of how we are able to scale the capability to do data science without hiring twice as many data scientists to solve the same problems. So, and this is one way to solve AI shortage in the region. No, it's gonna jump like 5 slides ahead. I have like 50 more, so don't please. It's dangerous. It's dangerous. Hey. Yeah. So, first of all, there are many ways to solve AI shortage. You can hire a bunch of people. You can train your existing people to do machine learning. But to be really efficient, you need to give tools to people so that they can focus on what they are good at and they can be really productive. And also focus on 2080. If you know that solving this thing will help to do twice as much, do it. focus on the first things and foremost, and not about building the fanciest stuff or the coolest stuff. Because not everybody has the resources of huge tech companies, not everybody has hundreds of engineers. So that's the way of thinking what you should do today to make your team better tomorrow. And you've seen how many people raised their hand when they said they have machine learning model in production. I mean, I'm not going to ask who actually have deployed the model and developed, but you can imagine that here there are a lot of people who have great experience and we should utilize it. We are in a small country and that's why we have to be really, really efficient. We need to optimize what can be optimized. We need to automate what can be automated. And for that, we need to share experience. So if you do have an idea, what about? Gotta get this exposure. So if you do have an idea of what you want to talk about, please approach the North Star AI team, organize your own meetup, share the knowledge in the format that's suitable to you. So please do. And also, we want to make this meetup series better. So please use the QR code, go to the link, give the feedback. This thing will stay on the screen. So please give the feedback, tell about what things you would like to hear about. And if you want to give a talk yourself, please approach and write whatever email, stuff. Yeah. So at Bolt, we are building top tech company in Europe. We have a lot of challenges in engineering and data science. And building data science platform here is a pretty exciting challenge, and there are many, many more things to go. So this is a sweet spot where you can have a lot of impact. You can architect new solutions that will stay for many, many years and will make many people happy. So check out our careers page, talk to us, and thank you very much. And the social convention tells me that I should say questions. Questions? Yeah.
Let's wait. It's coming.
I'm sorry for standing on stage. You talked about storage pressures that you have with Redis. Typically with RAM, it's going to be 5 to 10 times faster than NVMe storage, but it's also more expensive. Have you looked at sharding Redis on memory versus sharding on NVMe? NVMe storage, it's like hard drives. It can go to 3.5 gigabytes a second.
I guess we can Google it up. That's what the meetup is all about. So I think that at this point, it wasn't the problem. So there are different challenges. And when we talk about scaling data science, it might mean scaling your cluster, getting more machines, or getting lower latency. But to us, like the problem number one is how to make people productive. So that's kind of the 2080. I don't know actually how much it would store us. I think we are pretty happy right now with the Redis setup. And maybe if we have like much more data, we would go the way that Elasticsearch is the primary storage of features, and Redis we just cache the ones that are used frequently. But there are many ways how we can optimize for. We have like quite a good roadmap for this service and many others. So there's a way to start there. NVMe. Be sure to write it down.
So I'm afraid to switch. Okay.
Thanks for that. I actually see a potential issue of feature store. So let's try to. Okay, right. 1, 2, 3. Okay. So let's try to be closer to reality and see some pressure of it. Just imagine I'm a data scientist. I'm engineering and creating some like features, and I'm creating the code for that. So I'm actually owner of that. Then there's some really complicated ones, and business is growing, creating new functionality, services, new kinds of payments appear, and so on. So data scientists actually have to maintain this code and be sure that it continues working in a year and just like this. Do you see some lack of efficiency in that?
Right. So the question is, yes, right. Yeah, that's because of the audio. So it's still analog world. We are in digital era, but this is still like kind of old school tech. So the question is that data scientists develop features and they have to own them, they have to maintain them. The data changes, for example, some columns are dropped, some tables are normalized, and that happens all the time. Yeah, the question is, well, you do need to have features, right? You cannot deal without it. And it's much better to have them all in one place, incubate at least, and have a feature owner. If the person lives to another company, somebody has to take it on. But usually, it's the way we go is that there is a curated list of kind of resources, of dashboards, for example, that we have in our BI tools. And this is just kind of as code base. I mean, you have code in your software, and it still has to be maintained so it works in a year. So in this way, the features are just the code that has to be, it's more fluent because if the data changes, the code has to change. That is true, but that's also true for many services. And it's much better to have all the features or majority of the features in some one place where it's easy to find them, easy to verify that they're fine, than have them scattered through like 50 microservices. It's much, much easier. But yeah, thanks. Yay. Maybe we can.
Maybe I can do without it.
Yeah. Okay. Thank you for the talk. Just wanted to ask, what's the lag between the production system and the first step was Redshift? Why I'm asking is that if the feature store is always lagged, does that mean that if you want to do kind of machine learning algorithm, want to put real-time machine learning algorithm into production, then you need to recode all the features that you were using in that algorithm?
So that's actually the question of 38. So for example, in the case of ETA prediction, when we predict the time, we do need to know where our drivers right now in real time. And we have like high requirements because this low latency service, this is something that users see and this affects their experience heavily. That's why in these cases, like I don't say that all the machine learning goes into feature store. That's to be clear. We have many different models and many different problems. And some of them fit really well into feature store, kind of paradigm. Some of them don't. But right now, yeah, that's right. Sometimes when we need real time, we go the way of production database. When we have close to real time, for example, aggregates, but still we need like lower latency that we have right now with the features, we will use streams. We'll use like Kafka or like SNS that we have right now to compute this. But many of the features actually don't change as fast, like except the real time use cases. And the way that, for example, like some of my acquaintances have done it large tech companies is that you have a flavor of feature. For example, currently we can call it feature on data warehouse. It runs SQL to store the data in data warehouse from the data warehouse, whatever. What we could have is that you can have a Spark streaming code. So the same feature store, the same paradigm, but it executes different jobs with different latency requirements. So right now, we didn't have such an urgent need for that, but it still fits in the feature store paradigm. You just write not your SQL, but you write your Spark or Flink, whatever job you have, and integrate it with all the info. So that's a really good question. But the important thing is that you don't always need real time, and that's a mistake that many people do. Yeah, they're always. Oh.
Thanks for the previous question. That was my question. But so your stuff is relying on Redshift, which is your data warehouse. Does your regular analytic payloads work also in the same Redshift cluster, or you have a separate one for feature store?
We have just the same. It used the way that kind of our Redshift is quite powerful. That's why when we do feature computation, it actually doesn't affect everything else because we have, for example, separation. We have kind of connection pool, so to say, or queue pool, so that we are separating the request from our BI tools from the tools like from our services requesting, and that's how we can be sure that we're not gonna exhaust all the power of Redshift during the computation, so other people can still work. Also, a simple way to manage it and without having to have two clusters.
So more questions? If you have more questions related to that, I'm the person to talk with.
Yeah, sure. Well, so the question is how long we're going to stay on Redshift for. Right now, we are pretty happy with it. So it solves our problems, and it's not too complicated to maintain. And that's why, I don't know for how long. Like, I don't know, it's probably the larger decision. So I don't know, it has a lot of value, and we are happy to pay for this value. Yeah, sure. All right then. There is still some lemonades. I see. I don't know. I think you already had all the beer.
There's something better. There are pizzas already here. Someone has to
Alright.
eat them. So,
Well, that's the question. It was a data scientist. I'm not gonna show the finger on the person. Let's imagine it was me. Are there not enough seats? There are many more chairs which are not unused, actually. All right. So then, thank you very much for staying until the end, and we got a pizza.